probability that, this is the event that an interval jk is bounded by little x on both ends, but little x occurs nowhere in the middle. So, clearly, since the processes are ergodic, the probability of the union over all jk of ajk, so the probability of, if I take all possible j and k, the probability of all of these possible events happening, this is basically the probability of the universe, so that's equal to 1. So the left-hand side, I can rewrite this as, actually it's probably smarter to do this, to write the 1 on the left. So the union over all j and k, these are disjoint events, so therefore the union over all j and k, basically what I'm doing is I'm summing over j and k. So, because of the way I've set this up, equality is not possible between j and k. So I can have k equals 0 to infinity and j equals 1 to infinity of the probability of the individual events ajk. So this is equal to the sum from j equals 1 to infinity, sum k equals 0 to infinity. Now remember what I had in the statement of the lemma. I had probability. Well, this is similar. It's not exactly the same. Probability u minus j equals u. UL not equal to u for minus j is less than L less than k, given UK. What am I doing? This, I shouldn't be using u. I was using x. My apologies. X minus j is equal to little x. XL is not equal to little x for minus j less than L less than k, given UK is equal to xk is equal to little x. So this is quite similar to what we had in the statement of the lemma. To make it equal to this, this is the joint event of these and this, so I have to multiply by times probability xk equals little x. So I continue up here. Now, because this is stationary, because I said this is stationary, the time statistics don't depend on the particular indices. So in fact, I can shift this to, I can shift this into, question.
I think why you multiply it with the xk equal to x?
Because this is the joint probability of x minus j equals little x, xl not equal to x over this range. Excuse me. This is the joint probability of this, this, and this together. What I've written here is, this is just Bayes' rule, probability of this and this given that times the probability of that. So together, so it's like this. Probability A, B, C is equal to probability of A and B given C times the probability.
So the pattern occurs in history based on it occurs now, so the probability it occurs now is multiplied at t.
Correct. this. X minus I equals little x. L is not equal to little x for minus I less than L less than 0, given x0 equals x. That's the form that I had in the theorem, in the lemma. So what I'm going to do is I'm just going to simply shift this to the left by k. In that case, I get x minus j plus k is equal to little x. XL is not x from minus j plus k to 0, given that x0 is equal to x. I can do this. I can make this direct substitution into here because it's stationary. If it's stationary, then the specific indices don't matter, just their relative indices with respect to each other. So this is equal to, and remember that this is equal to qx of j plus k by the notation in the lemma. So this is equal to sum j equals 1 to infinity, sum k equals 0 to infinity of probability xk equals little x and cube little x of j plus k. Now what's more, this I can also invoke the stationary argument. This does not depend on k. It should be constant for all k. So I can call this x0 and I can take that out because it should be equal for all k. Now, the last step here, it would be nice to boil this down to a sum over just one index. So, I mean, a lot of these terms will recur because j plus k can only take so many values. So let's boil this down to, well, actually, let's see what's possible. So, along the vertical axis, let's put k, and horizontal, let's put j. So k can go from 0, 1, 2, 3, and so on. J can go from 1, 2, 3, 4, and so on. So what are the possible sums here? Well, I can have 1, 2, 3, 4, 2, 3, 4, 5. At the intersections here, I'm just putting the sums. 3, 4, 5, 6, 4, 5, 6, 7, so on. So if I look at this, how many times does each sum occur? In other words, each possible value of j and k. 1 occurs once, 2 occurs twice, 3 occurs 3 times, 4 occurs 4 times, and so on. You can actually construct a more formal argument to show that this is true. But therefore, this must be equal to probability x0 is equal to x times the sum. If I substitute this for a particular integer, I can sum from over all the possible results of j plus k. This is the sum from I equals 1 to infinity of I times qx of I. Finally, what is I times qx of I? I is the amount of time, so qx of I, remember,
Expected value of time.